Okay, good morning, class. Can everyone see the screen and hear?
Yes, sir.
Okay, good. All right, so as you know, I think this chapter is called Newton's Laws of Motion, something like that. There's only one new formula, really, and it's F equal ma, and it's a familiar formula because we used it last semester, I believe, right? Good. These problems, like most of the problems that you find in this course, are pretty easy. You just apply the formula, use your rudimentary algebra skills, and just solve basic problems, right? Sometimes some problems require a little bit of thinking and reasoning, but beyond that, it's not too hard. Okay, so let's start with the first one. A 3 megagram, supposed to put the word mass in there or something. Mass is traveling at 40 kilometers per hour on a level road. It is brought to rest with a uniform retardation in 10 seconds. Calculate A, the retarding force in kilonewtons, and B, distance traveled during retardation. Okay. So first thing we need to look at is we see 40 kilometers per hour. Okay. And we see kilonewtons. We know newtons is kg meters. Right? So we know that we need this acceleration to be in meters per second at least, right? And we're going to divide that by time. So we can see ahead, we can look ahead and know that, okay, maybe we need to convert this velocity. Okay, good. So converting that from 40 kilometers per hour to meters per second, we get 11.111. How we get this is very simple. 40 multiply by 1,000 and we divide by 3,600. This is going to give us that 11.111, which is here meters per second. Okay, good. Now, what is the deceleration? So what happens to this mass or car, whatever it was in the question? I forgot to write that part when I was typing out the question, right? So it's traveling at 40 kilometers per hour on the road, and it's brought to rest uniformly. So it goes from 40 down to 0. So the final velocity is 0, and we know from our formula v is equal to u plus at, right? Final v is equal to 0. That should be equal to our 40 kilometers per hour, but remember we converted it. So it's 11.111 plus a, which is the acceleration we want to find, and t, which is 10 seconds, because it was brought to us uniformly in 10 seconds. So it went from 40 to 0 in a time of 10 seconds, right? So times 10. Shift this around, right? We're going to get our 11.111 divided by 10, which is equal to 8, which is what we want to find. And that's what we do here, right? We took a little shortcut, we manipulate the formula, and we got this thing, right? Okay. So we divide 11.111 by 10, right? That's going to give it 1.111, right? Meters per second squared. Now we know the law. We know F is equal to M by A, where M is the mass, right? Mass, and A is acceleration. So therefore, the retarding force in kilonewtons, because this truck or car or moving mass, whatever it's called, is 3 megagrams, the force needed to slow that down is, of course, a function of how much we're trying to slow it down, the acceleration, and how much it weighs, right? So plug those values in. 3 megagrams and 1.11 meters per second, all right? Now we know 1 Newton is equal to 1 kg meters per second squared, right? Mass is usually measured in kg and acceleration in meters per second squared, right? So 1 Newton, that's 1 Newton. Now 1 kilonewton is 1,000 newtons, right? 1 kilonewton, 1,000 newtons. Is that? So essentially what that is 1,000 kg meters per second squared. Now, alternatively, you can write this as 1 megagram meters per second squared, right? Which coincidentally is the units we have here, right? So we can go ahead and just multiply them, okay? We can go ahead and just multiply them and say that the answer is 3.33 kilonewtons. Alternatively, right? If you want to show your steps, you want to keep it in standard units and convert back. You can say 3 megagrams is 3,000 kilograms, and then multiply that by 1.111, and then get your answer in newtons, right? And then divide by 1,000 to get kilonewtons again, right? Whichever way you want to work it, both's fine. Continuing onward to the other part of the question, B, the distance traveled during retardation. So while slowing down, while retarding, right, this vehicle traveled some distance. So again, it started as 40 kilometers per hour, which we converted, and then ramped down to 0, right? But it took 10 seconds to do that, right? And within that time, it traveled some distance. What is that distance? Well, we know our formula for distance. S is equal to UT plus half AT squared. We plug our values in. We know U is 40 kilometers per hour, which we converted to 11.111. Time is 10 seconds. Acceleration is 1.111. And of course, the acceleration is slowing the vehicle down, retarding, decelerating, bringing it to rest. So we put the minus sign. Okay. Plugging our values into the formula. Using our calculator, just type everything in if you want, or type it in piece by piece, however you want to do it. You should get your answer as being 55.56 meters. Okay, and that's the distance traveled during retardation while bringing the body to rest. Are there any questions on this?
Yeah. Yeah. 5 mo calculate. 5 mo calculate. Yeah.
Does
Kaya na.
anyone have a question? People just talking. All right, good.
No, sir, not from me.
All right, good. So no questions. All right, remember to mute your mic if you're not speaking. All right, good. So no questions. The answers are here. You can review it on your own time, right? Let's move on. Number 9. Calculate the resistive force required to reduce the speed of a 200 kg mass at a uniform rate from 15 meters per second to 5 meters per second in 2 minutes. Okay. So we know resistive force, F, the one force formula we know. We don't know a lot. We know 1, F is equal to MA. What do we need to find force? Well, we need a mass, okay, 200 kg, that's good. And we need an acceleration. We don't have acceleration. we have some changes in velocity, 15 and 5, and we have a time, so we can use that to find acceleration, right? So finding acceleration, we have two velocities, an initial and a final, and we have a time. So what formula gives us that? Well, it's the same old one, V is equal to U plus AT. All right, moving it around, V minus U is equal to AT. V minus U divided by T is equal to A. Great. Okay. Plug our values in. So the calculated resistive force required to reduce the speed of a 200 kg mass at uniform rate from 15 meters per second to 5 meters per second. So the initial velocity is 15 meters per second. Here, 15 meters per second. And the final velocity is 5 meters per second. Okay, good. Let me just run this number back through a calculator. Make sure it's right. Okay, great. So before I send the handout out, I'll have to make a change here, right? So anywho, the final velocity is 5. The initial velocity is 15. 5 minus 15 is negative 10. And we divide that by time, right? Time, 2 minutes is 120 seconds. Minus 10 divided by 120 is going to give us negative 0.08333. Okay? Now, we need to remember that we're reducing the speed, so that's why we got this negative sign, right? It's a negative acceleration, it's decelerating, right? So the answer again is minus 0.08333 meters per second squared. Okay, now, using this, with our F is equal to ma, right? We know again the mass is 200 kgs. We simply just multiply that by the acceleration. And then we get the force is equal to 16.67 newtons, right? These answers are right. I just made a typo here when I typed 10 instead of typing 15. All right, good. And that's it. Just use the two formulas, plug the new acceleration in with the mass that was given to us, calculate it, and we get F is equal to 16.67 newtons. Any questions?
No, sir.
Moving on. Number 10. Okay. So number 10 is a bit different. All right, but let's just jump into it. Number 10. Calculate the force exerted on the floor of a lift by a person having a mass of 80 kilograms when the lift is A, ascending, and B, descending with an acceleration of 1.5 meters per second squared in each case. All right. So before we go into this question, let's just review Newton's third law. Newton's third law states that for every action, there is an equal and opposite reaction. Okay. And this applies directly to someone standing on the floor of an elevator. Let's pretend this is an elevator, right? And there's someone standing on it. This person's weight is going to apply a force of 80 kilograms, of course, by the gravitational constant, down onto the floor, and then the floor is going to apply back another force equal to this, let's call it W, right? Is going to apply a force back up equal to that, so that this thing here remains stationary, right? It's in equilibrium. So equal and opposite forces. Keep that in mind as you work this question. So what's the stationary force? Well, or stationary force, or we could just call that weight of the person, right? So the stationary force, the stationary normal force of the elevator floor being applied back up. Or what's the force the person exerts onto the lift? So F is equal to MA, right? We multiply our 80 kilograms times our gravitational constant, right? 9.81 meters per second squared. Plug this into our calculator, we get 784.8 newtons. Okay, good. Now, this is when the elevator is stationary, right? It's not moving. Person's there, right? Some force is being applied downward. That force is being met back, right? Let's call that first weight. Now, in order to accelerate the person, right, we need to overcome this force and apply additional force to accelerate the person upwards, right? So we need some additional force, right? Some additional force. What is that additional force? Well, the person weighs 80 kg. In order to accelerate 80 kg 1.5 meters per second, we can calculate that force. So F is equal to MA. In order to accelerate 80 kgs 1.5 meters per second, we're going to need 120 newtons of force. Let's multiply 80 kgs times 1.5 and we get 120 newtons. So this person is stationary. For this elevator to move this person upwards, it's going to have to overcome their weight and apply that additional force, right? Right? So what do? The force exerted on the floor when ascending is equal to the weight of that person minus, plus the extra force needed to accelerate them. So we can just add, right? We get 784.8 plus 120 newtons, right? 784.8 plus 120 newtons. And that's going to give you 904.8 newtons. And it's that simple. Now, when it's descending, we subtract. Why is that? Well, again, Newton's third law. So again, the elevator is here. Okay, good. Now, in order to accelerate the 80 kg mass at a rate of 1.5 meters per second square, we need 120 newtons, right? Now, this person is applying his weight downwards, right? This 784 newtons downwards. Now, the elevator is pushing back up with 784 newtons when it's stationary, right? Now, in order to accelerate downwards, what the elevator can do is just be like, let's just give up 120 newtons. Like, let's push less, right? Let's push a bit less. And the net result, what's going to happen is that this force here, right? We're going to break this up into 664.8. That's being pushed back up, right? Because remember the elevator let go of 120 newtons. And that 120 newtons is going to push downwards, causing this body to accelerate downwards, right? So essentially, the force on the floor is going to be less, right? You're going to feel a bit lighter. So I don't know, maybe if you ever been on a roller coaster, right? When you're accelerating downwards, right? Your body feels lighter, right? You feel it like in your stomach or in your groin. It feels lighter, or maybe you're on the highway, right? You're going up Suicide Highway and you're going down that hill really fast. Your body kind of feels lighter, feels as if you're floating upwards. Well, it's just because the force being accelerated, being applied onto the floor is less because you're moving through space like that. All right. So what we do, long story short, when descending, we subtract that force, right? So 784.8 minus 120 newtons, which is equal to 664.8 newtons. And that's it. That's the force exerted on the floor when descending. Okay, any questions? Does this make sense? I hope so. Yeah, good. So no questions. All right. Now, Mr. Sill worked it a slightly different way. And you can go ahead and look at that, right? And try and compare the two, right? But logically, it's still the same thing, still the same formulas. And the end result is the same, right? Okay. So since you guys understand everything, don't really have a lot of questions. Okay, I'll work number 11 and then I'll give you guys the work number 12. How's that sound? All right, let me work number 11. Number 11. A mass of 25 kg initially at rest is lifted 30 meters by means of a rope of negligible mass at an acceleration of 2 meters per second squared. Calculate A, tension in the rope, and B, time taken to lift the load. So two things, tension, time taken. Tension, what is tension? Force. Okay, tension, force. Okay, good. So first and foremost, what is the weight of this mass? The mass is a 25 kg mass. The weight of it is 25 kg times the gravitational constant, 9.81, which is equal to 245.25 newtons. Right? Now, in order to accelerate the body, right, the additional force needed to accelerate that body, we get that 25 kg times 2 meters per second squared, which is 50 newtons. Great. Now, we're accelerating a body. It's rest, negligible mass. Okay, here's plus. So we're accelerating at 2 meters per second, right? F is equal to 25 kg times 2 meters per second, which is equal to 50 newtons. So now the tension in the rope is obviously that weight at 245.25 newtons plus this 50 newtons. Adding them up, we get F is equal to 295.25 newtons. Okay, just like the elevator and the person ascending, we're gonna have use some additional force to accelerate the body upwards, right? So we add these two up. We overcome the weight and we accelerate them. Okay, good. And that's it. That's tension in the rope. Tension, force. Okay, good. Now the time taken to lift the load, we were given a distance, right? A mass of 25 kg initially at rest is lifted 30 meters by means of a rope of negligible mass. So 30 meters, acceleration 2 meters per second, right? Keeping that in mind, we pull out our distance formula. S is equal to UT plus half AT squared. Now U, remember the body is initially at rest. So U is 0. S, the distance is 30 meters. So that's equal to half AT squared. Now T is our unknown. Great. A was given to us as 2 meters per second, right? From up here. From the question, 2 meters per second. Transposing this, all right? This is equal to 30, which is equal to half of 2 is 1 times T squared, right? So T squared. So therefore T is equal to root of 30, right? T is equal to root of 30. The square root of 30 is 5.477 seconds. 5.477 seconds. Okay, and that's all. That's the time taken to lift the load. Okay, any questions? No. All right, good. So now, continuing on to number 12, you guys can go ahead and work this. And if you get any issues, let me know. All right, so let me read it out for you guys real quick. A block of iron hangs from a spring balance. When the block is stationary, the reading on the balance is 65 newtons. When the block is hauled vertically upwards with a uniform acceleration, the reading on the balance is 72 newtons. What is the value of acceleration? Now, we need to do is think it through, right? Remember, F is equal to MA, right? We were given 65 newtons when it's stationary. So how can we go backwards, right? And figure this thing out? How can we figure out weight? How can we figure out acceleration not needed to move that weight, right? Think it through and tell me whether or not you get the same answer, right? So take about maybe 10 minutes on that.
Sir, sir.
Okay.
Yes, sir. I got the answer. The same 1.05.
Okay, good. Did anyone else finish and get the answers?
Yes, sir.
All right, good. So it's
Yes,
easy.
sir.
You just kind of reverse engineer. You take the concepts from the old one and you just work backwards and put it in. Yeah, good. So it shouldn't be too hard. Yeah, you just take the 65 newtons, you divide that by 9.81, right? Finding what the mass would be, and then, right, you find out the additional force used to accelerate the body, right? So 72 newtons minus 65, that should give you 7 newtons, right? Then you take the 7 newtons and the mass, so F is equal to MA, right? You found the mass, you found the 7 newtons, right? So now we can find what acceleration it was moving at, right? So it's just working backwards. Okay. Let's move on to number 15. Then we'll just call it today. Okay. So a pit cage having a mass of 2 megagrams is being lowered from rest down a shaft and accelerates uniformly until 20 meters from the top when the velocity is 400 meters per minute. Calculate the force in the rope just above the cage. If the cage, just above the cage, if the cage is then brought to rest uniformly from the speed of 400 meters per minute in 20 meters, what is now the force in the rope? So this question asks a lot, and there's a lot of things going on. All right, so first thing we should do, we see 400 meters per minute. Let's just convert that. 400 meters per minute. To get that in meters per second, we divide 400 by 60. Okay, and then we get 6.667 meters per second. That's the first thing we do. Okay, good. So what did they want us to calculate? The force in the rope just above the cage. Okay, force. First, we need an acceleration. All right, from the speed is given to us. 20 meters is given to us. So we have a distance, S. We have a velocity, V. And U, because it's brought to rest, right? And we have that's about it, right? So we don't have any time, no time. So that should tell us we need to use the formula without time, right? We need to use that V squared is equal to U squared plus 2AS formula. For a question like this, it's just one that you need to read over and really figure out what are they trying to say. All right, good. So V squared is equal to U squared plus 2AS. We already did a little conversion here, which is nice. Okay, good. So now the initial velocity is 400 meters per minute, which is this 6.667, and it's brought to rest. So we know that 0 is equal to 6.667 squared plus 2 AS. And we can carry over, right? We get minus 6.667 squared is equal to 2 AS. And that minus, what that's going to do is essentially just determine whether or not this is a negative or positive acceleration, right? Okay, and we know it's bringing it to rest, so it's slowing down, so it's a negative one, right? Okay, good. Now 2AS, S is given to us as 20, right? It's slowing down at 20 meters. We plug that in here. 2AS, 2 times A times 20 2 times 20 is 40. So we just divide the 6.667 squared by 40. Okay, plug that into a calculator, right? We use some algebra here. We get A is equal to 1.111 meters per second squared, right? And the sign basically just tells us whether or not we're accelerating or decelerating, right? Good. Now, the weight of the mass is F is equal to MA. The pit cage, right? Pit cage having a mass of 2 megagrams. 2 megagrams. Right? We do 2 megagrams times 9.81. Instantaneously, we're going to get that in kilonewtons. Why? Because megagrams, right? Megagrams, 2000 kg, which is going to lead us to 1,000 newtons, right? Which is so automatically just kilonewtons, right? So 2 times 9.81 is 19.62 kilonewtons. Kilonewtons because megagrams. Now, the additional force needed to accelerate the body, we found the acceleration, right? We found the acceleration. So using that, what's the additional force? Well, last time 2 megagrams times the acceleration should give us 2.222 kilonewtons. Again, kilonewtons because megagrams, right? Now, the tension in the rope when descending, accelerating the body, right? Remember, when we're descending, lowering it, we subtract, just like the elevator problem, 19.62 kilonewtons minus 2.22 kilonewtons should give us 17.398 kilonewtons. Oh, this here should be. Okay. So we're descending and we subtract, all right? Okay. 19.62 kilonewtons minus 2.22 kilonewtons should give us 17.398 kilonewtons. Now, the second part of the question is that we're still descending, okay? So we have this pit cage, this thing, and all the time it's descending, right? It's descending. But when, for the first half, let's say there's the same 20 meters gap in between, right? For the first 20 meters, what we're doing is we're descending while accelerating the body at a rate of 1.11 meters per second. For the second half, we're descending, but we're slowing the body down, right? And bring it to rest in 20 meters per second. So we're still descending, but in this part here, right, we're putting less tension on the rope, less force, right, causing the body to accelerate here. And in this part here, the second half, we're putting more tension in the rope. Essentially, we're trying to pull it back up, right? It's like we're trying to pull it back up, decelerating the body, right? Trying to slow it back down. So it's like we have this pit cage, and then we drop it, and it's accelerating down. And then at some point, we like tighten up the rope a little bit so that it slows down. So it accelerates up, and then it slows down, right? 20 meters each. So when we're descending but decelerating the body, we add, right? So F is equal to 19.62 kilonewtons plus 2.22 kilonewtons, which is equal to 21.842 kilonewtons. Does this part make sense, right? We're descending but decelerating the body, right? Here we were descending but accelerating the body. Does that make sense? Any questions on this question?
Sir, could please go it over one more time?
Yeah, for sure. All right, let's read the question. So a pit cage having a mass of 2 megagrams. It's coming here. So some pit cage, some cage. The mass 2 megagrams is being lowered from rest down a shaft and accelerates uniformly 20 meters until 20 meters from the top. Right? So here, let's call it the top. 20 meters from the top. 20 meters, right? From top. 20 meters from the top. Okay, good. Now, it accelerates uniformly until 20 meters from the top, right? When the velocity is 400 meters per minute. So at here, this point here, the velocity is this 400 meters per minute, right? Velocity. Let's keep distances on this side and velocity on this side, right? Now, calculate the force in the rope just above the cage if it is then brought to rest uniformly from the speed of 400 meters per minute in 20 meters, right? So it's coming back down from 400 meters per minute to rest, right? To rest. So it's coming back down. So here the velocity is 0. So it's initially at rest, right? And it accelerates up during this point uniformly, of course, to 400 meters per minute. And at this point here, it slows back down to 0 meters per minute or meters per second. All right. And it does that in an additional time of 20 meters. So this here, right, is another 20 meters, which is technically 40 meters from top. So what does the speed look like? Let's say, right, some distance here, distance traveled and velocity, right? So distance S, velocity V. So velocity starts at 0, cranks up to 400, then goes back down. This is at 20 meters, and this here is at 40 meters. 40 meters, but delta S is equal to 20 meters. This should make sense. So what we find is that because it's uniform like this, right? The acceleration in both sides, we're going from essentially 0 to 400 meters per minute and then back down. So 400 meters per minute, right? Going from 0 to 400 meters per minute and going from 400 to 0 meters per minute would require the same acceleration, right? Acceleration is going to be the same because these are two symmetrical. This is a symmetrical graph, right? So what do we do? Okay. Let's come back to our formula here, right? How do I get more candles? And let me erase some stuff. So the graph is there. Now let's look at the formula. So we established two things. We're going from 0 to 400 and then from 400 to 0. Right? Remember, we converted this 400 to 6.667 meters per second, right? 6.667 meters per second. Meters per second. Okay, good. So now formula is v squared is equal to u squared plus 2as. Okay, good. So now in one case, v is going to be 0. Let's take this case here. V is going to be 0 and u is going to be that 6.667 squared, right? When we carry it over, that's going to be minus 6.667 squared divided by 2as. S is 20. S is 20. So 2 AS, 2 times 20 is 40, right? And that's equal to whatever answer is, right? 1.111 meters per second. Now, in the other case, right? In the other case, this top case here, U is 0 and V is now the 6.667, right? So we don't need to carry over. We just get 6.667 divided by 40. And what you notice is that this minus sign kind of disappears. So it just depends. If we're going from here to here, we're accelerating. So there's no minus sign. It's just 1.111. And when we're going from here to here, it's the same 1.111, but with a minus sign. So we're accelerating and decelerating. It's the same value, like, right? It's the same value if we absolute value it, but it just has like a different sign depending on which half we're looking at, right? So that's essentially here. Okay. Now, the weight of the mass, of course, we need to know when analyzing the problem what the weight of the mass is. So let's make some more space. Let's make some more space. Okay, so the cage, boom, 2 megagrams, right? 2 megagrams. Its force downwards is going to be 2 megagrams times 2 times 9.81. This is going to go to kilonewtons, right? Megagrams, kilonewtons. So that's 9 to 18, 19.62 kilonewtons, all right? Something like that. Let me check. 19.62 kilonewtons. Okay. And this is accelerating downwards. All right. So it's descending, right? Descending. So it's going down. And just like the elevator with the person inside, remember, we're not trying to pull this person up. We're trying to drop this person down, right? So it's going to be this 19.62 kilonewtons minus the force needed to accelerate them, right? So the force needed to accelerate them is F is equal to M A. A we found as that 1.111. The mass is the same 2 megagrams, right? So that's this part here. So we found 19.62. We do 2 megagrams times 1.111 meters per second, right? Which is 2.22 kilonewtons. 2.22 kilonewtons. Let me erase that. So the additional force needed to accelerate it like that, right, is 2.22 kilonewtons, right? But remember, we're dropping it down. So it's the same way as going down the highway, right? You kind of feel light, right? The force exerted on the floor, or the force that's pulling on the rope, in this case, because it's a cage, so it's slightly different. We're gonna have to subtract, right? Okay, so 19.62 kilonewtons minus 2.22 kilonewtons, right? So going this way, the tension on the rope is slightly less. So we can call that T1. Okay? Tension in the rope when descending, accelerating the body, is equal to 17.398 kilonewtons. Now, the tension in the rope when descending, decelerating the body. So now when we're descending, decelerating the body, remember this body from this point to this point, right here, it's moving at a pace, right? It has some speed in it, right? 400 meters per minute. So now we need to slow that down. We need to apply the brakes, right? In order to apply the brakes, it's going to be like if you were stationary and you were going up in the elevator, but instead we're descending, right? We're still lowering in the cage, right? We're descending, but we're decelerating the body. We're applying the brakes. In order to apply that brakes, at that uniform deceleration, right? Uniform here, right? Uniform deceleration, right? We need to add, right? So it's kind of like ascending, but we're descending, decelerating the body. So that is 19.62 kilonewtons plus 2.22 kilonewtons, which is 21.842 kilonewtons, right? Descending, decelerating the body. Okay, Christopher, go ahead.
Good day, sir. You can have a class tomorrow, tutorial.
Yeah, we'll do another class.
All right. You can make me working. I didn't hear nothing you said. It just that.
Okay, all right. Anyone else? Do you guys understand what I'm saying? Descending, decelerating the body, right?
Yes, sir.
The body is moving at a pace. So you're trying to apply the brakes, you're trying to slow it down.
So you could use this as a rule of thumb, or you can always change depending on the case. Like whenever you're decelerating, you add, and whenever you're accelerating, you minus.
It depends. You need to analyze it, right? In this case, we are decelerating, yeah, and we do add, but in the case of the elevator, right, we're ascending, right? We're ascending, right? We're ascending and we're accelerating, right? Because you move from stationary and you're accelerating upwards, right? You're
Yeah.
not decelerating here, but you still need to add, right? You need to add your weight plus the force needed to move you from stationary, right? Because you're moving from 0 going up to whatever pace you need to go up to.
Yeah, I guess you know. So.
So you're adding there. So in this case, you're ascending and accelerating, right? So you need to add. Here you're descending and decelerating, so you need to add. So it just depends on what you're trying to do. You need to look at it and think it through. Okay. When is the next test for you guys?
Probably next week. Not sure.
Okay.
Week
All right,
after
so
next, probably.
go home. I need to make some changes to this handout. I think I forgot the word in one of these questions here. A 3 megagram something is traveling, and a sign here, I need to change this to 15. But after I do that, I'll send this out to you guys. All right, good. Hopefully I didn't confuse you guys too much, and you kind of get a little bit more intuition on how this question works, right? It is kind of a involved question, right? Like it's worded in a way that kind of makes you need to think about what is actually going on, what this person is trying to say, right? But when you get all that, right, you can clearly see that the answers are these two, right? Descending,
I understand.
accelerating the body, and descending, decelerating the body. All right, good. So that's all I have for you guys. If you don't have any more questions, you can go ahead and leave. Stop the recording. Someone saying something.
Yes, so I want to know if you finished marking the test.
No, I have not. I only marked a few, I think 20. I still have 100 more to mark. So please be patient, right? I will get to you in like maybe 2 days, right? So I'll start marking tonight and tomorrow. Right, so just give me 2 days. I didn't get a chance to mark this entire weekend, all right?
Sir, have you been posting anything? Because for this course, I haven't seen any video being posted on YouTube.
Really? I did
The
post
videos are
projectile.
there. The videos are there, sir.
Yeah, good. So I have a MEC 1214. That one's not labeled because I know what to label it. And this one's projectiles and projectiles from Tuesday. So one was a Wednesday class and one was a Tuesday class. Right? We only had 3 classes and there are 3 videos. Two of them are the same thing, projectiles and projectiles. All right, so just click into the channel and look at MEC 1214, right there. This here is from another class, so don't worry about that. Very good. So the videos are here. Just click into the channel and you'll see them. Good. All right. No other questions?